Hello everyone, I'm Jiayue from the program of Data Science. Today I will introduce my data science project, forecasting electricity demand during COVID-19. My supervisor is Dr. Metro. The first part is about background and motivations. Firstly, nowadays, along with the people living standard enhancement, people's demand and dependence on electricity are deepening. So, if we can find the regularity of electricity load, we can arrange electricity load more reasonably. To make a better decision in power systems operation, it is necessary to forecast the electricity demand, which can guarantee the equilibrium between consumption and production at any time. Secondly, particularly in early 2020, the COVID pandemic has spread quickly all over the world. The power systems were highly affected by the COVID-19 related shutdowns, and strict mitigation measures were carried on at that time. Also, it was found that although there was a decline in the thermal energy demand of the buildings, there was an increase in the electricity demand. At the same time, the rush time of it changed. Thus, these changes can cause financial risks, aggravating the bad economic impacts of the COVID-19. The second part is about the project aim. First, we will do data visualization to show the relationship between variables with electricity load. Second, it is time to validate whether the proposed methods, including persistence model, generalized additive model, random forest, and gradient boosting machine model, can predict the load accurately. Third, we will study whether multimodal ensembles can have a better performance than each model itself. Last, we will look for the adjusted models which can decrease the bias of the aggregation model. Then I will say something about the state of the art. There have been several techniques applied to forecast the electricity load, including the linear regression, autoregressive, integrated moving average, and neutral networks. In a competition, there were two teams from the top three champions using the multimodal ensembles. Then I will shortly introduce the selected models and their advantages. The first is the persistence model, which only uses the data 1 week ago instead of including the variables in the dataset. Second, the generalized additive model can effectively take up this challenge because it is a flexible regression model, which is widely used in industrial and scientific applications. It can model the relation between the response distribution and several covariates non-parametrically. Third, random forest is a non-parametric statistical method which can deal with this prediction problem. It is widely used in a variety of fields as it has an excellent predictive performance. Fourth, gradient boosting machine model can be a good method to make the prediction. The reason is that it combines various base learners. Each time of the learning, the learner can decrease the loss to fit the data better. Then I will introduce the results. For the first aim, we made plots of load distribution and its association with variables. We found that the load usage dropped rapidly after COVID, both at each day of the week and at each time of the day on average. And the load is low at weekend and between 0 o'clock and 5 o'clock at a day, partially because people choose to relax instead of going to work at this time. As it comes to the relationship, temperature seems to have a positive relationship with the load, probably because when it is hotter, there is a greater need to maintain the operation of the machines. In addition, when pressure or humidity increases, there will be more heavy cloud cover. For the second aim, when it comes to the persistence model, we can see that during post-COVID, the residuals are above zero most of the time, which means the model underestimated the load and it has a low bias. Later, for another 3 models, we included all variables in the dataset. What's more, day of the week, day of the year, and time of the day were included to better analyze the load change with time. When analyzing the GM model itself, we can conclude that wind direction is not important, so as pressure, wind speed, and cloud cover. The load reaches the peak around September at afternoon and at 80 of humidity. The residuals are higher than those of the persistence model. As it comes to the random forest, load of last day, time of the day, and day of the week are top 3 important variables. So we can see that the time-related variables are considerable. In the afternoon, the residuals reach the peak both before and after COVID, and those before COVID are larger. On Monday, the residuals are the lowest and they increase during the week. And the plot in the right shows that the overall residuals after the COVID are even higher. As it comes to the GBM, load of the last day, time of the day, and day of the week are also top 3 important variables. On weekdays, the load has a high level while the load utility reduces at weekends. Between 7 o'clock to 20 o'clock, the load has a high and stable level, while the load utility is low between 0 o'clock to 7 o'clock. Between 10 and 25 degrees, the load increases with the increase of the temperature. After 25 degrees, the load remains a high and stable level. The overall residuals are similar to those of the GAM. For the third M, we can see that the square loss of the samples is lower than all single models, which means it has the best performance. Although the persistence model has a high square loss, it is the only model that underestimates the load and has a low bias, while the residuals of the other models always increase with time. Therefore, the persistence model always shares the biggest weight with time, and we will try to optimize the other models later. For the fourth M, we add another game model which only uses data of the last month. Luckily, RMAE is lower than before, and after its adding to the combined model, the residuals become lower. Now, both the persistence model and the game of the last month model account for a big weight. Thanks for your listening, and thanks for the guidance of my supervisor, Dr. Metro. He gave me a lot of advice during my work, and I'm thankful to all lecturers in this master program. I learned a lot during the last year.